Okay, so this is going to be the first problem since the guy I sent it to didn't ever solve it. I wanted to give him a very simple problem and see if he could solve this problem. There's only 3 questions. Now, I didn't write the words down, but if he looks back at the question, it'll tell you find the total resistance. Second, that's part A. Part B is find the total current. Well, find the current, which is the only one current. There's only one source, one path here. And wants me to find each individual voltage drop across these elements. And wants me to find the total power and the power across this resistor. The resistor that has 18 ohms. All right. So if you notice, we have a DC source and we only have resistors. We don't have capacitors, we don't have inductors, and we don't have an alternating current source. We have a direct current source. So this voltage has the polarity marked here. This is the way the circuit looks on the diagram. It gives you the fact that the current's flowing from negative to positive. So it's going to hit from this negative, it's going to this positive node, or this positive load, this positive part of the load, and then it's going to come over here, and then over here, and then back to the ground. So it's just going to go in this direction. So this is our current. There's only one current. The total resistance, we can add all these up together, and that would be our total resistance. 12 plus 18 is 30, and 30 plus 10 is 40. So RT, that's easy. It's 40 ohms. Now we want to find the total current. Ohm's law is voltage is equal to the product of current resistance. So if I want to find current, I need to divide both sides by R. And we have the voltage and we have the resistance. Now, I don't have my calculator handy with me, so I'm going to try to do this by hand. 40 goes into 72. Once. And then we get 3, 2, and then that goes into that 8 times, so 1.8 amps. 8, 16, 24, 32, right? So this is 1.8 amps. Each one of these resistors has 1.8 amps flowing through it. We can find the voltage drop across each one of these. And when we add all those voltage drops up together, it has to equal 72 volts. So let's find V1. V1 is 10 ohms. And let's use this equation. V1 is equal to the current, which is the same, 1.8 amps times 10 ohms. That would be 18 amps, or 18 volts. We got 18 volts across R1. What about R2? Well, V2, that's going to be equal to 1.8 times 12, with the 12 on the top. Now, when you're dealing with decimal values, it's best to just bring it down when you're done with it. So, pretty sure. And just to show you whether you're doing this right or wrong, because I always mess this up. I like to do it this way. I like to get rid of the decimal point. So let's multiply both sides by 10, because in the end, we're going to have to divide by 10. So let's remake this 120 and this 18. Okay. So now I got to figure this out. So 18 into 120. If I take this times 5, that's 50, and 50 and 8, that's 90. And so we can go up one more. So 6. So 60 and 6 and 8 is 48. So it's 108. So we got 108. So we got 6 up here and 108. And then we got 12 here. Whoops. 12. And then we bring another 0 down and we get another 6. And this is just going to keep repeating, actually, because this will be 108, and this will be 12, and another 120. So it would be 66.7 volts. That's not right. If this is 18 volts, it should be close to that. Well, 12 divided by 2 is 6. So it's going to be a little bit higher than, it's going to be 6 point, and I'm dividing by 10. That's what it is. I forgot to divide by 10. So this answer is divided by 10. So it'd be 6.67 volts. This is 6.67 volts. Okay. Now V3 is actually going to be pretty convenient for us to find the power for E. But the V3, that's going to be 1.8 amps times 18. But let's not go that far. Okay, let's not make it that complicated. We could do this more simply by taking 72 minus 18 minus 6.67, and that'll equal V3. Because Kirchhoff's voltage, or Kirchhoff's current law, says that sum of the voltages in, or voltage law, sum of the voltages in is equal to sum of the voltages out. This is a bad representation of a sigma symbol. And what happens is whenever you subtract the V out from both sides, you're left with a negative sign on this V out over here, but then you get 0 on this other side. So this is what we're doing. We're this expression is no different than this expression. And 72 minus 18, that's 54, and 54 minus 6 is 48, and 48 minus 67 is 47.33, or 47.33. So we should get 47.3 volts right there. Now I do have my calculator right here, actually. So I'm going to make sure I did my math right. 120 divided by 1.8. Oops. 120. Well, it's actually 12 divided by 1.8. So yeah, 6.67. And let's do 18 times 1.8. 32.4. So this number was wrong. I did that one wrong. I thought I did it wrong. That's why I got my calculator. But 72 minus 18 is 54, and 54 minus 6.67. Yeah, so where did I... 18 times 1.8, 32.4. This is 32.4 volts, which doesn't make sense. This is 10 times 1.8 is 18 volts. 12 times 1.8 is I did this wrong right here. This is 21.6 volts. See, this is a good way to go back and check your work after you've done it, just to make sure you did not make an assumption. I am not sure how I got that first number. When I watched this video, after reviewing and editing it, I might be able to figure out what I did wrong. And if I do, I might add the clip in. But that is 32.4 volts. And if I take 72 minus 18 minus 21.6, I get 32.4 volts. So we've already established that this is 18 volts, 21.6 volts, and 32.4 volts. And we should be able to, 10 ohms, 12 ohms, this is going to push more current back. So we're going to get a bigger voltage drop on that second one than we will the first. Likewise, we got more resistance here. We're going to have less current, more voltage. Let's see here. Now the power could be done a certain way. Power is actually equal to voltage times current. But if you don't have one of these values, if you have resistance instead, you could rewrite this as I squared times R, because IR is V, and you have one more I there because you have the product of I and I. But it's also V squared divided by R, because V divided by R is I, and I times the V gives you the power. So we can do this several different ways, but the easiest way is just to take the total voltage times the total current, which is equal to, make sure I put amps in here. Now, calculator makes it easier. I could divide this by 5 and then multiply whatever that value is times 8. And add it to 72 times 10. Now, what did I just do? I just broke down the process there of the multiplication and not the simplification, but the multiplication. 129.6. And this is in watts. Watts is a unit of power, but that's the total power. What about right here? Well, I could just use the ohms resistance. Let's take the total current, 1.8 amps times 18 squared. Oh no, I squared. It's I squared times R. I squared, 1.8 amps squared times 18. That's going to be 58.32. Okay, now I could do the same thing by taking 72 squared and divide that by 18. Oh, not 72 squared, sorry. The voltage drop across V3, which is 32.4. I square 32.4 volts, which is 1049.76 volts squared, and divide that by 18 ohms, get 58.32, same value. So there's two different ways. You could do the 32 volts squared divided by 18 to get this value, or you could take the 1.8 amps squared times this value to get this. Or you could take this value, no, you can't do that. You could take the total power after you've gotten these two powers and subtract the sum of these two from that total power of the circuit to get this value. But that would take much more work than what we already did. But this just solves a simple series circuit. The second problem I sent him, I believe it was just a simple parallel circuit, and I'll do that one next. All right. Now this is the more complicated part because we're dealing with a parallel circuit and not a series circuit.